All right, so our last talk of the day is Johannes Buchner. Take it away, Johannes.
Thanks. I will be talking about how we use machine learning, not versus Bayes. It's kind of clickbait title. Of course, we use them together in large-scale surveys, in particular how we do demographic studies with the new satellite eROSITA. And this is a collaboration of a large team of people and whose work I will be referencing. So our main question is how galaxies and their supermassive black holes are interacting. So you could imagine the galaxy gas is feeding the supermassive black hole, activating them as AGN. And so they grow, and we want to ask when do these galaxies activate their black holes, and under which circumstances does this happen? And then, in turn, what does this do to the host galaxies? How does it impact them? What does it do, for example, to the star formation in these galaxies? This process is very complicated. It's multi-scale. It also has a time delay aspect to it that you see in the bottom plot there. The AGN gets triggered, but the effect you see in a different wavelength at a different time. And it's a highly stochastic process as well, so we cannot probe it directly. So our approach is to use multi-wavelength surveys to statistically probe this with biased samples, but to get the underlying population, taking into account our selection biases. So how do you go about this? Well, you could imagine one model, that's the blue one, where you say, okay, gas comes close to the supermassive black hole, it activates the AGN, the luminosity goes up, at the same time the obscuration goes up, so that you have a simple correlation between those two. Or you could imagine a very complex stochastic model, which is the purple one, that is all over the place. And how do you distinguish between those two now? Well, you could ask, well, in this green box there, how often do I find AGN in that particular state? Right? So what's the number of AGN in a cubic megaparsec that are in there? And so we go out, we count them essentially, and at the same time we know that faint AGN and those that are heavily obscured are harder to find, so we have a selection effect there that we have to model in. And that's a nice thing about X-ray surveys, that we understand the selection effect very well. For AGN, it's a quite pure selection. This is how we can get the demographics of the underlying population. And so if you want to find the fastest growing black holes, those are the most luminous quasars, you have to go to very large area surveys and try to find them. And the way to do that is eROSITA is an all-sky survey of the sky in the X-rays, deepest survey in that particular band so far. And what it does is it spins around its axis and observes part of the sky, and it co-rotates with the Earth-Moon system around the sun. So every 6 months you cover the entire sky, and that survey is being performed several times. Here you see the first all-sky image produced in the X-rays by eROSITA, and there's lots of information here and lots of science you can do. I will talk about the AGN. All these white dots that you see everywhere, most of them are AGN. About 1 million have been detected in the first all-sky survey. And there are more to come, making it deeper and deeper. And so you see we have lots of objects, and now we want to study when these supermassive black holes are growing and in which galaxies. So here's basically the outline how these multi-wavelength surveys proceed. In this case, we have the X-ray data taken, we have a detection procedure. I will not talk about that, but you have some significant detections. And then you want to not just use the X-ray information, but all the multi-wavelength information you have, right? So you have the optical surveys, the infrared surveys, and you sort of have to marry them together with some approach. Once you have this multi-wavelength data, you can classify the sources into AGN, stars, and whatever else there is. Finally, for the AGN that I'm particularly interested in, you analyze these particular objects for example, the redshift, for their accretion rate, for the stellar mass, and so forth. And finally, you can ask, well, now that I have for each object a posterior distribution of its quantities, what is their underlying population distribution in these parameters. And for that, you also need the survey sensitivity that comes in from your detection procedure. So finally, we get to the product that we want. And now, how do we use machine learning in this? Well, all over the place, and I will try to highlight some of these aspects. But first, I want to say that we are using here a framework that infers parameters of this population distribution. Essentially, it's an extended Poisson likely or posterior, and people are getting more and more excited about this approach. But essentially, what you have is the number of expected sources given your population distribution, integrated over your sensitivity to some particular parameters like luminosity and so forth. And on the left-hand side, or on the left here, you have for each object what is its likelihood, or posterior in this case actually. And that per object analysis contains of your likelihood and how often you find these according to your population model. And so if we split up that likelihood a bit more, that contains, for example, of the X-ray data and your multi-wavelength data. So for example, the X-ray spectral analysis and the photons. And now you see there is a bit of an issue here because you have to sort of bring those data together, right? And so how do you combine for each X-ray object? How do you find what belongs in the infrared surveys, for example? And so you basically have the likelihood from your X-rays multiplied with the probability that any of the other surveys has a counterpart for that particular object. And then you iterate through those options. Each of those options has a probability. And then you get to use the likelihood of that other survey. And how do you do that? Well, we've developed a code called NWay, which exactly computes these probabilities. And in the general case, you can imagine for 2 surveys, you already have k combinations that you have. But as you have more and more catalogs, and in many cases we have 4 or 5 catalogs, you have an exponential growth of these combinations. So that's a little bit worrisome, but you can actually compute the posterior there analytically, and you can take into account additional information. And this is what this slide is about. So usually we have in the X-rays quite a large uncertainty of our position, and in the background you see the images in the B, Z, and near-infrared K band. And now the question is, which of those objects that you see there is the right object corresponding to that X-ray source? And NWay enumerates all these possibilities, and what it does then is it also allows you not just using the distance of these objects to assign a probability, but also to use multi-wavelength information, what might be the likely counterpart. And so here you see a plot of Wise colors versus Wise magnitude of X-ray sources in gray, and all kinds of other non-X-ray sources in the yellow. And you see they have different colors, and so you can train, for example, a machine learning tool to classify between them and assign the ones that are more behaving like X-ray sources, assign those options a higher probability. And we know, in fact, from many decades now of X-ray surveys, that the K band is a really good way of picking up X-ray emitting AGN, for example. And so this can be extended, of course. In the latest work, Julian Wolf has been working on making a random forest, not just taking a bunch of features, but actually using 6 magnitudes, which then amounts to training on the entire SCD. So then I don't really want to talk about classification, because that's pretty often talked about, or photoses. I think template-based methods are still the state of the art according to that recent review. For the X-ray analysis, I want to briefly mention that you have to remove basically a background contamination there. And what people have traditionally done is to handcraft these models that have a bunch of components and fit them to some background region, and then use that model to model it in the source region. What Charlotte Simmons did is to develop a PCA model trained on X-ray archives across the many archives we have now from various X-ray satellites. And then based on the PCA components, you have a machine-learned parametric model which you can then fit to any individual data set. And so again, this is a machine learning approach to overcome these handcrafted models. A similar situation is on the demographics. How do you actually get population distributions? We don't really know a priori how these distributions are supposed to look like. So for example, here, the luminosity function. So here on the x-axis is luminosity, how it behaves as a function of redshift or stellar mass and so forth. We don't want to impose that. So people have moved away from handcrafted functions that evolve with some recipe to, for example, Gaussian mixture models. I've been working on Gaussian processes, or Gaussian process-inspired methods, and neural networks are also being used as inspiration. I don't have time to talk about nested sampling, although I really like it. But what I want to mention is that even in our inference algorithms, we nowadays use machine learning to make them more efficient to sample in regions that are more likely to be of interest. So for example, UltraNest uses a method called ML friends to find the region of sampling. So just coming to my summary, I kind of like to stay in a consistent Bayesian inference framework where you model the selection effects. You go from a biased sample to learn about the underlying demographics. And I think it's good to work in physically meaningful parameters, and to use physical models when we trust them, when we think they are meaningful, when we care about them. But it's also very helpful to use these probabilistic machine learning tools when we might not particularly care about some particular component, or we have difficulty parameterizing them. And that's a very powerful way to go about it. Here I have a bunch of tools listed that are quite popular for the analysis of surveys these days that you can check out on multi-wavelength cross-matching, on X-ray spectral analysis, and general purpose inference. Thanks.
Fantastic. Thank you so much. That's a great talk to end the day. Do we have a few questions on the audience? Here, Anya.
Hi, thanks very much for a very nice talk. Sorry, could you say what is ablation studies? What do you mean by that?
Yes, that's a very important thing to know when you do machine learning. It's a standard procedure to basically take off components of your model to learn what is the most important components of your model. So imagine you have, I don't know, a convolutional network with 10 layers. You take away one layer, or you take away a way of doing it to understand, is that particular aspect of the way you built your inference procedure, is that particular aspect important? So you take away various things until your model really fails. Ablation studies is quite important.
No other questions? If you can think of other questions, either the Slack channel or you can ask Johannes at the coffee break. So let's thank again all of the speakers of this afternoon.